Hello, everyone. Welcome and thank you for joining us for today's RoboNation webinar on systems engineering. Today's lineup features members of Team Inspiration, including mentor Alex Szeto, who brings decades of aerospace and systems engineering experience, Colin, who is deeply involved in robotics and has competed at RobotX, RoboSub, and RoboBoat, and Carina Dumitrasu, a team lead this year at RoboSub. Whether systems engineering is brand new for you or something that you've already got incorporated, this session is for you. Please drop any questions into the chat. And with that, I'm going to turn it over to Team Inspiration.
Welcome. My name is Alex Szeto. And Katie mentioned I work in aerospace industry for 39 years and have been mentoring robotic teams since 2011. You will learn a lot more story about our team, either from at this presentation and at our team website. Next page, please. So with this, what we have, even though I have a lot of experienced system engineer, but I also bring Colin Szeto and Carina at the presentation. They will do more discussion talking. Colin have been competing in RoboNation since 2019. Actually, he have been competing robotics since 2011. He has been a speaker in COSI presentation in COSI International Council of System Engineers, so he is very experienced. So he and I will bring different perspective, right? Someone has been working 39 years in aerospace, specialized in system engineer, but Colin have been working since 2020 like a system engineer, so he has 6 years experience working for Northrop Grumman and L3Harris. And Carina is our newest team member, starting this year, January this year. She went to RoboBoat competition in Florida and also is our current RoboSub lead. What she learned in a very short time, she actually had never done robotics before, but she had learned from RoboNation, RoboBoat, and right now is the team lead of RoboSub. She actually earned an internship with Seabike, a local marine industry company, and retrofitting 2 commercial RoboSub. If you have any question, both of them can talk more about the system engineer. And the reason we have this panel presentation, each of us will bring different perspective, right? Someone just learning about system engineers, someone has 6 years experience, and someone 30 year experience, right? So hopefully the presentation will give you inside perspective. So I won't be saying something that say you will say, what is Alex talking about, right? But then yeah, someone Colin have been working for 6 years and Carina just new, so they will bring a different perspective. Next, please. So, Colin.
Yeah, every single team, whether it be commercial industry partners or even robotics teams, always face a dilemma, and you may also too. Every single sub-team working in isolation, executing their part to the best of their ability, but when it comes down to crunch time, 2 weeks before, a week before competition, before a deadline, nothing comes together. It's not necessarily something that happens to just student teams or just industry professionals, but happens to all of us. So what to do now? In this slide, we have a component versus a systems approach. We have this hypothetical on the left of if each sub-team in designing an aircraft optimize their system, only considering their requirements or their preferences. You can see a structural sub-team would make a plane out of I-beams. Comms sub-team would put antennas all over their plane, right? And then on the right, you can see when a team comes together, implements systems engineering, follows the process, you can come off a product that comes off the production line and serves the world, right? We see the F-35 there. Systems engineering really we're striving for clear communication and balance amongst different groups, and to implement all the requirements different stakeholders bring. So why systems engineering? In traditional design, some folks call it waterfall method, where you start with an idea, work on one part, and then the next, and then the next. There's a component focus. There's a local optimization of, oh, I want to make this part of the system the best part. There's a sequence of work. You don't progress until you finished, let's say, stage 1 before you go on to stage 2, as well as there's possibly a late problem discovery. Systems engineering strives to address all of these challenges at the forefront, thinking about the entire system in its entirety, optimizing every part of the system, as well as integrating the work into the decision matrix, decisions, and hopefully through all that, you're going to be discovering the problem as early as possible to really guide your decision-making process. So all in all, this will reduce risks, improve reliability, lead to better performance, and reduce the total cost across the life cycle.
Carina?
Today, we're going to be discussing what is systems engineering, go over the systems engineering V model, our requirements, interface, trade studies, verification and validation, applicability, and then we'll answer some questions that people have.
Oh, by the way, if anyone have question, depending on question, if the question you ask is something we already on the later chart, we will tell you that we will adjust a little bit later. But if you have any question you don't understand, you're welcome to ask question, right? We want to make this as interactive as possible, and any question is fair, and we will do our best to adjust. If we cannot adjust, we will provide link, and after the meeting, or that we will provide backup information.
So what is systems engineering? It's an interdisciplinary approach that enables the realization of successful systems. Some key purposes is managing complexity, integrating diverse engineering disciplines, as well as meeting stakeholders' need with an emphasis on balance across performance, cost, schedule, and risk. The idea here is that a system must be optimized as a whole, not as a collection of implemented independent parts. And historically, it was piloted to support space exploration missions as well as the moon landing. You can see the concept of operations on the right side. The landers would have to go through multiple different orbits, and every single lander has a swath of different components, and all of these components need to play nice together before the final product reaches its destination. So large aerospace programs spearheaded this, and we look forward to provide some illumination on the process, as well as some tangible tools for you to implement systems engineering into your own robotics teams.
Yeah, and I want to add on something. Back on the chat, Colin. So a lot of time when you're working on a system, right, you're looking at the picture, right? The picture on the left, lower left is the Apollo astronaut riding a rover on the moon. But when we think about system engineering, we think a much, much bigger picture, right? So before Apollo landing on the moon, and I was young enough at the time, I actually witnessed the lunar landing at the time when I was very young. So later, like I could join work, I become a aerospace engineer, right? But when you think about system, you think much, much bigger picture, right? So before people go on Apollo, putting astronaut on the moon, the picture on top, there's actually a surveyor that people don't hear much about. We actually send satellite to survey the moon, right? Take picture of the moon and including the landing, right? When Apollo program say, I want to land astronaut in this certain area, they actually send a surveyor, the program is landing on the moon to make sure collect the composition of the moon and make sure that when we send to an astronaut over there, they can survive. We also take the environment, right? I was very fortunate. Two of my manager actually, one worked on Apollo program and the one worked on the Surveyor program, right? The picture on the right is actually the Galileo spacecraft. You will see a Galileo spacecraft later. When we plan a mission to Jupiter, we just don't say, hey, I just fly directly to Jupiter, right? If you see the slingshot where they launch from Earth, it actually go to the Earth a couple times and go to Venus, and then using the gravitational pull to send the Galileo spacecraft to Jupiter. But a lot of time because of all this long mission, they also take advantage to see when they're going over there, they say, oh, by the way, I want to see some asteroid. So they went to see Gaspar and Ida, right? So when we talk about system engineer a long time ago, we're talking about major system with 100,000 company working together with over 100,000 people work together, right? That's when people say, I definitely want system engineer that I can bring everything together. But right now, they are so powerful, as you see later, then system engineer is applicable to what we are doing right now. It doesn't have to be a major program, right? It can be applicable to all different levels. Continue, Colin.
So what exactly is a system? A system is a collection of interacting elements organized to achieve a common purpose. Some examples can be RoboSub, RoboBoat, the drone, or even the Galileo spacecraft. Our systems are made up of different elements like the hardware, software, but it's also the people who are working on the system, the processes in place, the facilities that we use, and the information parsed between the teams. Our systems get more complex. They've also become a system of a system. So in RobotX, when we have our RoboBoat, RoboSub, and drone all working together to achieve one common goal for the whole system. Colin?
Systems engineering is a life cycle process. In this case, we're guiding all parts of the life cycle through requirements. Some considerations would be design, manufacturing, operations, maintenance, and disposal. It requires interdisciplinary collaboration against all the different subteams, such as hardware, electrical, and software. And it's important to verify and validate throughout the process to ensure stakeholder needs and the requirements are satisfied. In the confines of a year-long competition cycle for RoboNation programs, teams may experience design, manufacturing, and operations, and the life cycle may stop there, or they might continue to develop their insights into and spin it and take those lessons learned into the next competition cycle. So there's a theme of repetition here, and the idea is we build a robot to then build a better robot in the future seasons. But systems engineering is an end-to-end consideration, not just from a blank sheet of paper, but truly realizing it in the real world. We organize this life cycle with the systems engineering V model. We start at the top left, go down the V, and arrive on the top right. The first step always is to define the concept development or concept of operations, as well as the user needs. For us, it might be the students of the team, but for industry, it might be the maintainers or the operators that will be taking these vehicles into the real world. We then generate requirements as well as flow down these requirements to the component levels. Determine the architecture and interface between each different component. We then prototype to prove out concepts that we're unfamiliar with and utilize trade studies to decide what concept we want to pursue. We incorporate all of these ideas into a design review to make consensus across the team before we spearhead the modular and parallel development because we're on such a short time scale for these competitions, it's important to go in parallel. As the hardware is being brought up, the software team should be developing at the same time so that we can bring both components together to really push for that integration and testing time. We inform operations by starting with component testing, making sure every single individual item checks out, then move on to unit testing to ensure that each subsystem in isolation is operational. We then integrate everything into systems testing, and then we push it off to acceptance testing. Did we meet all of our requirements? You can see the V kind of has some rows going across from it, and it's an iterative cycle. So as you define your concept development and your user needs at the top left, you want to start thinking about the acceptance testing procedure on the corresponding row as well. It's not one-to-one, and during the entire process, like we mentioned, we want to think end-to-end, thinking about the whole system, thinking about each of the different considerations as we're developing the concept. So this involves a lot of reflection and iteration, and it's a repeating process. Requirements would be to translate stakeholder needs into things that are measurable. So these can be flowed down to 5 and 7 levels, all the way down to component level. Characteristic of a good requirement is that it's clear, it's measurable, it's testable, and it's traceable. The human language is really messy, and requirements writing takes a lot of practice to make sure that there's really not any other interpretation of what is required besides the requirement as written. An example of this, the sub or the autonomous underwater vehicle shall operate autonomously up to 8 hours at 50% thruster power. On the right, you can see for the ASV, there are different themes or buckets of requirements, and these buckets are just some recommendations, but they're requirements that apply to the mission, navigation, mechanical, electrical, software, and safety. And below that, there are requirements below those levels that can go down into increasing granularity. The requirements flow down needs to be specific and testable. An example of flowing down a requirement from level 1 all the way down to level 6 would be this power supply example. Level 1 is starting very broad. We're provided the team handbook during the season, and our RoboSub shall meet the handbook requirements. We'll use RoboSub and autonomous underwater vehicle, AUV, very interchangeably here. The AUV shall support 20 minutes of autonomous missions. That's an example of a qualification run. And we would like to take logs out of that. Level 3 would be the AUV power shall support 60 minutes, including pre and post autonomous mission operation to allow. And this is to inform judges to take a look at logs to make sure that they're scoring everything correctly. The AUV shall supply minimum voltage and amperage to support operation. TBD is there to really demonstrate that a lot of these ideas or the specifics can be drilled down at a later point in the V. The power subsystem shall provide voltage conversion to support 5 volt and 3.3 volt sensor power requirements. The voltage converter shall have a stable voltage with less than 0.2 volt fluctuation. So you can see how we start from the highest level, level 1, all the way down to level 6, so that we can inform component selection. And this is just an example of deriving lower level requirements from the high level. An example from a competition team, Team Minion from Embry-Riddle Aeronautical University in this past RoboBoat. They included this requirement in the appendix, and notice that they have a ID for each requirement. And this really drives home the traceability aspect so that you can reference a requirement in one of your artifacts or your design documentation submissions rather than restating the entire requirement.
With the requirements, it's also important to manage your interfaces. Most failure occurs between subsystems, whether that's hardware and hardware, hardware with software, software with software. It's important to note whether it's internal or external. It's the surface ID. What is the source and destination components, the protocol or the standard, what data is being exchanged, at what frequency or rate, and the error handling and timing requirements. An example of a hardware to hardware interface can be an I2C bus, which is between your microcontroller and your temperature sensor, where you then have to identify the signals and voltages being sent. An example of a software to software interface could be between your REST API and your web application, and the protocol, data format, and authentication that you then go between the two. It's important to define these interfaces early so that you can minimize testing issues later and understand where errors can occur. We utilize systems diagrams as visual indicators for the team, as well as to understand the larger system. For instance, we have electronic and paper versions. So when we're in the lab and pointing to a specific electronic component, I can then reference the entire system through the paper and mark it down, as well as using digital copies when someone's remote and also able to see the whole system.
Trade study is a important way of documenting your decision-making process throughout selection of the designs that you want to proceed with. It comprises of two parts, the weights as well as the ranking. The weights help convey the importance of the different attributes, what matters most to me. And then the ranking is a subjective or possibly data-driven measurement that the team selects in comparing all of the different designs. In here on the weights, you can see our greatest decision-making factor was the minimum amount of ports. And this applied to how many holes are actually in the penetrators, or excuse me, in the end caps for our AUV design selection, as well as the next most important metric was ease of fabrication. Through this, you can see that the dual enclosure won out in this decision matrix as it gained the most points. It's critical for the team to align on the desired features as well as the weighing factor before proceeding with the rankings. Here, for a more mechanical approach, we implemented the trade study in determining how we would want to access our electronics harnesses within the RobotX competition. Here we have made the attributes different mechanical considerations or attributes that the box would experience. And here the one that won out was a static mount trailer box for the ease of simplicity and ease of accessibility. And you can see on that right photo at Sarasota for the RobotX 2024 challenge, we are able to easily access the electronics as we decided in this decision matrix.
Yeah, on this chart, let's go back on one chart. It's very, very critical to identify the feature that is interest. Typically at work, what we do is we get the program together, right? Say, hey, this is the component we care about, right? Like more accessibility, modularity, right? Pick your choice, right? So typically, we brainstorm idea. Everyone has a voice. We just do a brainstorm activity, right? Everyone say, hey, this is all the thing I care about. Typically, for trade study, we try to limit to about 10 more critical one, because the critical one will drive will overshadow the smaller one anyway, right? So we typically, the criteria, we pick about 7 to 10. Typically, we don't do more than 10, not less than 7, because if you only do 1 or 2, then that's not much trade to talk about, right? And over here, everything we talk is all because the system we have is smaller. We primarily talk about the technical component, right? But in a actual real world, you may have schedule and cost in there also, for example, right? The schedule takes too long, right? It's because some of the connector, for some of the connector, you buy a connector, even you have money or some of the equipment, they take 3 months or to 6 months before you can buy it, right? Get it delivered to you, right? So it's very important to pick a good set of criteria, right? And when you pick it, make sure you're not biased, right? You say, hey, I want to bias on this and one system versus the other, right? And then after you select the criteria, right? Then you select the weighting factor, right? Basically, you look at that, say, after I select this criteria, which one is the most important? Which one I care more about? And then that's how you put the weighting factor on that, right? A lot of times we put the weighting factor to make it easier. We do a 100% weighting factor, and then we just divide between all the criteria, right? So on this one, we normalize that. If you add all the number up, it will be add up to 1, right? So 1, 10, or 100%, your choice, right? But that is where you say, all the criteria I care about, this one is more important. And then the rating number, you have individual, right? You just rate, right? In this case, we just rate 1 to 5, but after you rate it down, then you multiply the weighting factor to get your actual number. And that is where you have the average. Average, to some degree, we don't care much. We care more about the weight average, right? Because weight average will be your feature and what is the most important for you. Okay. Any question on a case study? Okay, continue, Colin, Carina.
2 more terms are verification, which is the idea of if we built the system right, it's comprised of component, unit, subsystem, and system level testing. Testing can come in different methods like inspection, visually ensuring that it's passing requirements. So for instance, for safety, analysis, demonstration, and then also testing. Validation focuses on if we built the right system, which focuses on the stakeholder needs.
Yeah, on the right side is a James Webb Space Telescope. Colin worked for Northrop Grumman before. I also worked for Northrop Grumman. James Webb Space Telescope is an amazing system that built by Northrop Grumman together with many other companies. The picture on the bottom is when they were looking at the sky where stars generating. So one thing about working on systems, even we're working on robots and RoboX, right? At least for our team, before the James Webb Space Telescope launch, we actually took the team to visit the building of James Webb Space Telescope, right? When Colin and other team member was much younger. So what the verification validation is a very good example, right? Because this is just an amazing technology. That's where you really need to focus on your system engineering knowledge. And the other thing is, I want to share a story. One of my boss was working with the government before with the Navy, supporting Special Operations Force. One time they built a boat. The Navy say, hey, I want this small boat, can carry this many people, can carry this much equipment and all that, right? And then the company say, no problem, I know how to build that, right? They set up the company and they build everything, right? And then when the boat delivered to the Navy, and this is a small inflatable boat, right? And they say, hey, I make all the requirements, right? It can carry, I think at that time I forgot 7 or 10 people. It can carry that. It can carry additional 400-pound weight and all that, right? It had the range for the boat to travel, but the bottom was a net. And then the Navy would say, hey, why don't you give me a boat? The bottom is a net. Neck, basically open neck, the water can come up. And the company say, hey, you say the boat had to lightweight, had you go this far, had you carry all these people. I meet all the requirements, right? But then the Navy, sometimes it's very important, right? When you write a requirement, right? Make sure you don't miss the requirement, right? Make sure the people understand how it is used, right? Otherwise, the company can say, hey, this is the one I deliver. The other one is with Northrop Grumman, one of the program I work on. The company deliver a piece of equipment to the operations center. It met all the expectation. It was amazing capability on that. But at the same time, because that system was so complex, the operation require the operator with a PhD knowledge, right? But on the other hand, something at the time the company forgot that all the operator was a junior military enlistment with only several years experience, right? Because U.S. military, they are on a rotation program. They go. I saw the question I will answer, and they are on 3-year rotation, right? So basically, the operator cannot use the system. So even though we verify all the product, we meet all the requirements, but at the end, the user basically say, hey, you have to return the product. Okay, the question I saw that, how do we explain a system, how it you train RoboX? Colin, can you go back to the chart where we have the RoboX picture? So if you look at this picture, right? If you look at, some of us compete on RoboBoat, some of us compete on RoboSub, right? And then some of them doing the joint competition, right? So when a system, that's just individual system, right? When we define system and system, is the picture on the right, right? When you have 3 systems working together, the joint, the sub, and the boat. To some degree, we're also missing one element of the system. On this picture, you also show the ground aspect, right? But a lot of time we kind of like ground is already like RoboBoat, the boat and the ground is all together. But system and system, if all 3 of them have to work together, right? Some element, you definitely can just do the job by yourself, right? You say, hey, I do the job by myself. I don't care about the boat or the sub. But to get maximum point, all 3 of them, a lot of time have to work together, right? Like John and Bo. The John pass information to the Bo when they fly over the surface, taking the night flight. That's where you get more point to the Bo, right? Without the John, the Bo can do the basic core maneuver, seeing the light on the side, right? But on this disruptive maneuver, the drone had to detect the pattern, the light, right? And then send the information to the boat. And then that's how a system on system, they had to, a lot more communication, work together. And also a lot of time you also, when you do the system, you also complement each other. For example, in RoboX in 2022, we had a hyperspectral camera. Hyperspectral camera is a special camera detecting the chemical composition of the object, right? So for us, when we're computing in 2022, we say, if I need a camera to detect the missing object to identify which it was, right? We put the equipment on the drone to share the information to the boat, but the camera turned out to be pretty heavy. And if you put housing on that, it makes the drone much, much heavier. Some of the team actually say, even though it's a system or system competition, some of the, in 2022, 2 of the RoboX team, instead of put the camera on the drone, they just say, hey, I just put a very high mouse on a van V. A van V is a much bigger vehicle. They just mount the camera on top of the vehicle, on top of the boat to detect the object. So a lot of time when we talk about system, we negotiate a lot, say, which capability we want to work on what system to give me maximum benefit. I hope that answered your question. By 2024, 2026, the key part of the system will be the communication portion, how you handle the data on each, and also deciding which one is the best one to accomplish the objective. Colin, Carina, your question.
Can you read out the question, please?
Oh, okay. For Colin and Carina, what has your role been in your various competitions? And how have those roles helped you either in school, internship, or anything else you are doing now?
Sure, I'll go to the slide that has my photo on it. In this case, one of my roles this year, or excuse me, in 2023 was as a mechanical lead. And in this presentation to the judges, we truly identified how our decision making was traced all the way up to our level 1 requirements. Through leveraging this, we're actually able to meet a director at RoboNation when it was at Transdeck, and we're able to provide him a brief about how we leverage systems engineering to apply to our small scale, quick turnaround systems. Through this, making the connections, in-person connections at competitions, we're then able to augment my internship experience from, at that time, the mission systems portion of Northrop Grumman into the AS systems, the aeronautical systems part of Northrop Grumman. So that has been how just being there in person at competition, being able to talk about systems engineering, making it relatable to the engineering director at the time. That's how I've been able to land an internship and then continue to spin that into real world employment. Carina?
As in RoboBoat, I served as a supporting member where I learned about systems engineering and how the whole process works. And I would say in terms of leading the team now, it's definitely helped in terms of logistics alongside taking on a more leading role with the software. It's definitely helped me land my current internship with the connections through Team Inspiration as well as like on site. In terms of school, I would also say it's helped as I think looking at the whole system and being able to connect the way that you learn what you learn in school with the way that I can apply it to RoboSub.
And by the way, Carina is traveling to UC Berkeley to study her mechanical engineer. She's very happy about that, and we are very proud of her achievement. Right? So what she learned is actually help her to get different contribute for her getting accepted into University of California, Berkeley. Okay, another question from audience. Can you describe a time, either in competition or in real life, when you had to implement a system engineering model to help save a project or get it back on track?
I feel like this slide kind of ties into that partly. When our thruster went down and it stops working, we have to overhaul, take it out, and then unit test a new thruster with an ESC, verify that that thruster works, solder the dry mate connector, verify continuity, and then paw our dry mate connector, verify continuity again, and then integrate it on the benchtop ESC, and then we can integrate it with the full system. And I would say in this way, by systematically unit testing, we're able to ensure and have confidence in ourselves before we integrate it in the full system. And it also makes, if anything goes wrong, or something doesn't go the way that we wanted it to, it's really easy to trace back where the error happens and troubleshoot.
Okay, good.
One of my
okay.
experiences for implementing systems engineering to save a project, in this systems diagram, this was actually generated in 2025 RoboSub. The systems actually deviated so much from the physical configuration standpoint. We didn't actually have a representative model of the system. So through creating this and generating this model, we were able to identify what were the spare components that needed to be replaced, as well as what components were no longer available, whether it be custom or just no longer manufactured, and approaching the system from laying out everything, all the interconnect data rates, if you will, we're able to then systematically unit test individual components before integrating it back into the system.
For me, this Alex, a lot of time on I work on much major system like the example. I did not work on James Webb Space Telescope, but I work on Galileo and other major space program. So a lot of time is when things work well, then it's pretty easy, right? You just continue operation, right? When things doesn't work, that's where we rely on system engineering model. Right now, the system engineering model is just not a requirement by requirement. Right now, model-based system engineer, you actually can run a simulation on the model, right? You put all the requirements on there, and then you can drive down to say, hey, if this thing doesn't work, then you can drive down and say, what was the requirement? What was the test data? Was it the test result? And you can actually run a simulation model on that to say, it's almost like Monte Carlo simulation modeling. You can kind of troubleshoot, identify, right? So document, just like at work, or even the robots are RoboBot, RoboX, right? Document is last thing any engineer wants to do, but I cannot overemphasize document is so important that we actually train our team to do document, right? Because when something go wrong, you don't want to rely your memory and activity, right? You kind of like, when something go wrong, you can say, okay, let me find what the document, what's the tray, right? Just like Colin showed on this diagram, right? Interface diagram, right? The test data, test result, right? On a system engineering model, we actually, all the test data also say what the requirement also. So having able to check all those information, it actually will help to troubleshoot, say, a lot program, right? Because when I talk about program, I'm talking about million line of code, several thousand people working together, right? If you don't have a good model, when things go wrong, then you will say, all you can say is something went wrong, and it makes it very difficult. So a good model is important. Colin, got a question for you. For someone doing C-Perch right now, remote operate, we actually our team familiar with C-Perch. What would you recommend we do to prepare to move on to autonomous?
I recommend starting small. Yes, the maritime domain is important, but right now this would be a resource that our teams put together called the Monkey Bot. In this, you leveraging a Arduino as a low-level controller, as well as a Raspberry Pi as a high-level controller, you guys can quickly iterate on making autonomous maneuvers. And hey, you could even start bench testing where you set up your entire system on I guess, a piece of wood, a piece of paper, and you pretty much run it through its paces to see if your sensor data can actually speak well to the computer, and that would inform your mission planning. The theme here is to start small, just like the systems engineering V, with the unit component level, and then kind of build your understanding by hooking it up to an Arduino and then hooking that Arduino into a Raspberry Pi, hooking that Arduino up to different electronic speed controllers. And from starting small and growing each part of the system, you'll be able to create your technical depth as a foundation, and then you'll be able to integrate your requirements as well as systems thinking into developing your autonomous underwater vehicle.
Okay, the next question I will answer. The question is for educator and mentor who want to introduce system engineering earlier. How can they help students develop a system thinking mindset before they are formally learning system engineering? So to some degree, it's very similar to what Colin. Another question, are you aware of system engineering curriculum for high school students? I will answer that also. So for educator, right, if you want to talk about system engineering process, the V diagram could potentially be too much, but on the other hand, can you go to the chart of your team member, Colin? So this is the chart on the packet. Oh, by the way, this chart is available. After the presentation, you guys can have a copy of this chart. On this one, the first year our team competing in RoboSub actually 2019. At that year, there was a lot of teams. That's before COVID, 59 teams around the world and 55 university team, right? Team Inspiration actually only have 5 high school students and 9 middle school students. The middle school student ran from 6 to 8, 6, 7, 8. That's the US system in 5, right? And because we taught the system engineering concept, right? So the way we taught the system engineering concept is just make sure that they understand for young students, like then at that time, like Colin is in the fun lab. So you can start with that and say, hey, what do I need to do, right? Always start with requirement, right? They may not understand concept, operation, all that, right? You just start with hey, let's say what is the requirement, right? What do we want to build, right? And then as soon as you think about what to build, you say, okay, how do we need to test it, right? What is expectation, right? So that will be very, very basic system engineer say requirement and expectation, right? Colin, go back to your monkey bar. So this one monkey bar is actually more complicated, right? It's someone even middle school or elementary school. Our team does a lot of teaching, right? You can a very similar battery, right? Turn on the LED light, right? With a circuit card and all that, right? And then you build bigger and bigger. But the first thing you will share with the student will be, hey, what are the requirement, right? And then say what's the expectation now, right? If you want to put a circuit card, turn on an LED light, right? You can just use battery, turn on LED light, right? Something very simple for the student, but teach them say the requirement, expectation, and how do you test. That I would say that is the very, very simple V model, right? Concept, manufacturing, test, that will be a simple requirement test, right? If you want to talk about system engineering curriculum, we can help you. I actually don't know any system engineering curriculum. The closest one is the INCOSE. INCOSE more college professional, but if anyone wants to work on system engineering curriculum, I can work with you for high school students. One thing, we also have a very good presentation chart. When you go to Team Inspiration website in 2019, 2020, when Colin and his team first competed in RoboNation, RoboSub, we actually had a INCOSE system engineer presentation. You follow that presentation, that will work pretty well. Colin, go back, continue the presentation chart.
So this was in 2019. We were actually able to leverage systems thinking, systems engineering as a process to impart onto the judges our decision making. And this landed us a second place in the US and third in the world for static judging of the technical paper, technical presentation, and documentation. And this actually landed us the IEEE Innovation Award, which is quite humbling for a community-based high school, middle school robotics team.
And opportunity because of that, right? Go back on that chart. Yeah, because the recognition of that is actually open a lot more opportunity to us. 2019, 2020, they actually on the virtual RoboSub competition, they were the world champion, and then 2021 we get the Robo Expo that accelerate, right? So so one thing is system engineer can be taught at very different level. The curriculum is just simplified, right? Because you just get an inclusive handbook that will be completely overwhelmed, right? The grade school students say, I'm not going to read a 200-page handbook to learn system engineering, right? Start small. Next page. So the result, right? The team member, our RoboNation team member actually working in very industry. The youngest student we get some of the internship they get actually is a middle school. Colin have been teaching robotics in middle school. But the engineering internship, one of our student actually was 9th grader. And he actually, last year, he got an engineering internship with a local company, C-Bike. And then for Carina, this year, she also make a record. She only learned robotics for 4 months before landing the internship with C-Bike. And then if you look at that, right, we had the student work for different organization, company. This is some of the best. There's a lot more company here, but we just highlight some of the company that like SpaceX, Northrop Grumman. We actually had over 15 team members working at Northrop Grumman. And Android and NASA Jet Propulsion Power. So learning system engineer does open a world of opportunity for our students. So summary, right? System engineering process, right? Mindset, right? Should be in everyone's toolbox, right? So everything you do, right? I mean, it can be applicable to your family, right? Work is the requirement, right? Even cooking a dinner, right? What's the requirement, right? What's all the ingredients I need to put it together, how I put together, and what's the outcome, right? For all the team members, I recommend we train all team members to be a system thinker. Basically, every time you do it, tell them to think big picture, right? Northrop Grumman actually encourage every employee to be system thinker, and all the big companies doing that. And learning. But the most important is the third supporter, right? Learn and understand how to fit the piece to the overall system, right? So if you have a like CPERT, right? If you say mount the motor, right? You have to test and say how mounting the motor, right? You have free motor, right? How you mount the motor will affect the direction of travel, right? Do you mount the motor a certain way, up, down, right? If they mount the upward and downward, the motor to go up and go down, the motor has to mount very close to the center of the robot, right? Because you only have one motor, right? So basically, test then how the small piece fit into the overall system. With that, this is our last chart. But I do want to give credit to RoboNation. My team have been competing with a different competition before. First Global, Odyssey, Automai, Science, Olympia, and all that, right? But we really love RoboNation competition because, especially for our middle high school students, give them opportunity to learn on a lot more complex system and allow them to start working at internship. Most of our high school students had engineering internship during high school, And some of the new college students joining our team is also help them to get college internship very easy and transition to permanent employment. So I definitely give kudos to RoboNation for giving us a platform. And the bullet at the bottom, right? Learning system engineer is learning how and why does make engineering more fun. And having fun is very, very critical, right? Having fun is where they have the passion. They will work until late at night, early in the morning. Some of our students work 7 days a week because they have fun. But the most important is knowing how their peers fit into overall system will help the student to learn a lot more. And next, please. And so this is the link in COSI for all the mentor engineer or even young student. You can definitely go to INCOSI, that's International Council of System Engineer. They have all the information available about system engineering. RoboNation, I think most of you are aware, but for some people not aware, I just put RoboNation link there. They have all the different programs. Marine Technology Society is also very good. It's a worldwide organization and actually help our team a lot. Our team had done presentation at Marine Technology Society also. And that's how we connect to a lot of San Diego. We connect to a lot of ocean engineering company, give us opportunity, both a sponsorship, advice, mentoring, internship opportunity. LASA Jet Propulsion Lab is where I work. I have worked there before. Very fun. I highlight LASA Jet Propulsion Lab because they do autonomous vehicles, satellite, spacecraft, and all that. There's a lot of team. We work with a lot of other RoboNation team. I want to give a kudos to Bumblebee. They are one of the best of the best, and the other thing is they also very interested to share all the information. This year for the RoboSub competition, they actually share everything they have, what they did on the 2025 RoboSub. That's a team we can learn a lot from. If anyone want a contact, RoboNation has our email address, but if you go to teaminspiration.global, you can also contact us this way. And when we do robotic competition, we don't stop by the season. Like I know some CPR team, RoboSub team, RoboBo team, they can say, hey, my season finished, I will stop, right? For our team, we actually continue learning, right? As soon as RoboBo finish, we start thinking of next year. Or we go RoboBo, RoboSub, RoboAct, and then RoboBo, RoboSub, RoboAct, and also we also a team member doing the job as UAS. So learning, the best way to learn is don't stop, right? So just say, hey, I done RoboSub already, I done RoboBo already, I done CPR. I just stop, right? Start looking at the next area, right? For any team or any mentor or student say, I want to learn more, we are always available to share information, right? Colin actually have been working both a competitor and a mentor, right? Carina also have been teaching local STEM education, right? We actually support students across the world. Right now, Saturday, Sunday, we support students from Ecuador, Paraguay, Haiti, Eswatini, Togo, and Benin, right? 3 countries in North South America and Africa, right? The best way to learn is by teaching. I think we're almost up to time, but we are always available to answer any more questions if anyone wants to stay. If you have any more questions, ask.
I think you've got all the questions taken care of. Like Alex said, we are just about out of time. So thank you everyone for joining. Thank you so much to Alex, Colin, and Carina for bringing such a great mix of professional experience, competition insight, and student perspective to the RoboNation community today. Thank you so much, and we'll see you soon.